So, good morning, ladies and gentlemen. Finally, we get to the last lecture of this splendid course of advanced quantum mechanics. I have to be here. My camera is broken. What shall I say? It is a only lecture about relativistic quantum mechanics. In many universities, if you attend a course of advanced quantum mechanics, that will be exclusively relativistic quantum mechanics. We didn't have it much, and we've been kind of happy. So my initial idea would be just to skip relativistic mechanics. Because, well, we engineers, and we hardly see anything relativistic in our everyday life, and also in most of applications we use. Okay, but when I told so to my colleagues, they said, no healthy engineer would survive without knowledge of Dirac equation. So this course will be mostly about Dirac equation, with kind of funny derivation and with a discussion of it. And as far as applicability is concerned, as far as application is concerned, a kind of fun effect which I've learned during student times. Naively, you expect that most of our experience is non-relativistic, and you think that laws of non-relativistic quantum mechanics are experimentally verified in much larger extent than relativistic field. The truth is just opposite. It is relativistic mechanics which has been verified experimentally with kind of ultimate precision, much better than the laws of motion of actual metallic balls return. The reason is persistent interest and money pumped into particle accelerators, which is still going and which was for decades. So people have accelerated so many particles to ultra relativistic velocities that they accumulated much more experimental data than about the motion of actual mechanical particles, balls, whatever. Right, so it's also can be applied. And of course, when they build up these accelerators, they really go deep into quantum mechanics. They consider scattering of particles, trying to understand their structure. We don't go for that, but at least we will establish a theory of quantum fields today, relativistic quantum fields. Again, since we are kind of Fitzmarkers, since we're engineers, we do it in a little bit old-fashioned manner with a Hamiltonian, not with Lagrangian, how it's supposed to be done in other courses. But it's perfectly fine. It's just another method, which is more familiar for us, more intuitive for me, and has links to condensed matter physics I will outline shortly. Good, so that's why this course, relativistic quantum mechanics. Let us see where to start. Perhaps with this person. It's always good to look at personalities to understand what has happened in physics, what has happened with our knowledge. This person, Professor Minkowski, has been doing mathematics for 98% of his career. He did quite some contributions, but that time math was rather different. We would hardly remember him for mathematical contributions. At some stage, he kind of felt that he could change the topic, got some interesting mathematical problem to solve. And somebody told him, he was in Harvard, but at that time, physicists, strangely enough, discuss now some mathematical problems, rather fancy ones. So he began to attend seminars of professor of physics, and that was a good place. He quickly caught what was the issue by the time. They've been discussing mostly Maxwell equation and the symmetries and the like that. And since he didn't have usual stereotypes of a physicist, it was easy for him to make a real, perhaps biggest discovery for the whole history of humankind. And actually, he was not modest or humble about his achievements. He presented a talk at, how they called it, DFG, Deutsche Physikalische Gemeinschaft, whatever you call it. In the abstract of his talk, it was really written like this: I'm gonna present a greatest discovery which unites notions of space and time in one new entity. Right? So that's it. We live in Minkowski space, which has 4 dimensions, although we conveniently think about 3 dimensions of space and 1 dimension of time. This is not so. That's what he discovered, or whatever assumed. He was the first to state clearly that what you see in Maxwell equation is not about electricity, it's about the properties of space and time taken together. Interesting enough, because there was a kind of compensation law which has been taken place if has died in rather stupid fashion from illness, which usually people don't die. It was like in 3 weeks after he gave his talk. Yes. Around which time was this? That was, if I'm mistaken, 1905 or 1904. So it was very beginning of 20th century, before the war. Okay, so what was the statement actually? The statement was that we live in Minkowski space, and each point in this space, which is commonly called event, because it happens at certain position, certain time, it just for vector. It is not usual for vector we are familiar with. It's a bit special. This speciality is expressed like this. If we take 2 points and define the following quantity, which looks like a distance. And it could have been very convenient if you're plus here. Then it would be distance in 4-dimensional space. It's not, it's minus here. But this quantity for each two events remains invariant if you go to a different coordinate system, if you change your coordinate system. If you skip that, if you just live in 3-dimensional space, it would mean rather trivial thing. The length of 3D vector does not depend on the choice of coordinate system. Now we have also coordinate systems which move in time. And so the transformation includes velocity. And right, it changes. It's a bit pain in the, how shall I say, neck, that this, because of this minus. There are different ways to make it convenient. I'm gonna use rather old-fashioned way, when the time coordinate is taken to be purely imaginary. Then the invariant becomes sum of the squares. Good, fine. Let's see what we can do with coordinate systems, how we can think of coordinate systems, taken into account this discovery of Minkowski, take into account that this invariant should stay the same under transformation. So any change of the system is a transformation of a full vector, right? If it's rotation, it's a kind of, how say it, we call this matrix, orthogonal matrix. If it's not, this is a matrix of Lorentz transformation. Let us see how we can derive this matrix. Okay, first of all, this is definition of the matrix. So it has two indices, or in full glory, 16 matrix elements. And since this invariant must be constant, this matrix must satisfy this relation. What I did, I just computed square root of this, put it here for any vector. So for if this matrix satisfies this relation, then for any vector, input vector and output vector, invariants are the same. Good. So one can elaborate on a simple coordinate system, reference system, which moves in x-ray direction. How shall I say it? It moves in with a velocity c beta. It cannot move faster than light. Right? So beta is always smaller than 1. Okay, and then we have to transform only two variables, time and x3. And this is a matrix which we have. it diverges, each element of this matrix diverges if a speed of the reference system approaches speed of light. Shall we do some matrix some vector matrix multiplications? I think it's good. So let us see. Let us take simultaneous events. Two simultaneous events. Take the difference between them, so time is 0. And that is separated by L, the length. So let us find the answer. Let us see. That's gonna be L. That's gonna be minus D. No. Okay, that's our output vector. That's how this pair of events look in a coordinate system. Which moves with velocity c beta. All right. So eventually spatial component get longer. Let's go to a real relativistic problem. It's very bad that Star Trek is not relativistic. Okay, they have some special physics, very complex one. But let us assume that relativistic physics works in standard form. So this is a standard problem. You see a bed of prey, clean on chip. Length is 95 meters. And it passes by you with a velocity close to speed of light. And that's experimental picture. Snapshot. Something gets wrong. We just predicted that it becomes larger. Something is wrong. Whose idea? What is going on? Yes?
Before the frame was moving, and now I need to assume that the ship is moving. So it's
That's not true. Can take a picture of one. For two simultaneous events, if you look at it if the task near you, the spatial extent becomes large. That's correct statement. That's a problem which, with our intuition, is very difficult to forget about. When we make a snapshot, these events are simultaneous, but they're not simultaneous in the reference frame of clean on chip. That's why actually what we have to transform with the matrix lambda is a vector which has L, 95 meters, and some unknown delta t. In the answer, these events have to be simultaneous. And there is some L prime, which we observe. Okay, then if you do this algebra, if you solve for delta t, and you find delta L, which is indeed smaller than original one. Okay, so it's really kind of very difficult and counterintuitive point of relativistic quantum mechanics, which predicts everything. We just think about this. Yeah, for instance, people have Gemini paradox and things like that. If you want to dip into it, you can easily find some literature. Good. Relativistic mechanics, Minkowski space. Why people were so excited about discovery of Minkowski? Certainly not because of his personality or his mathematical merits. They, and in particular Einstein, understood that if you apply Minkowski principle, you can generate a variety of unusual physical laws and see the links where the links were not supposed to be. Kind of unification, which has been propagated by Albert Einstein. And it's better to understand how it's done if you just look at mass, if you look at symmetries given by this Lorentz transformations. Right. So what we have learned so far, there are quantities which are transformed as for vectors. There are different quantities which transform differently upon Lorentz transformation. A particular example is a scalar. How one can make a scalar given a vector? You just make in product of this. It is similar to what we do when computing the Minkowski invariant. So that's going to be scalar. There are more complex representations of Lorentz transformation group. We will look at it, at some of them. Let me just understand that Minkowski discovery implies that there are no three-dimensional vectors in physics. There are only four-dimensional vectors. So if you think that you have a physical quantity which is three-dimensional, you've got to find for the fourth component. Most known example is the energy momentum vector. Here it is. It characterizes the motion of a particle, and it is made from classical momentum vector, usual one, and this is a fourth component which is proportional to the energy. Right. It's written here explicitly in terms of velocity. We see that momentum is a kind of non-linear function of velocity. The same with energy. Right. And of course, very counterintuitive consequence of this, something that you know,
Only massless particles can travel at the speed of light. Only particles without mass can travel at the speed of light.
that is, but no, much simpler, something which you perhaps even before any education have seen in cartoons. Let me try to reproduce it, something like, let's see, you? No? MC squared. Biggest thing to swallow was that particle in rest do have energy. MC squared. Which is very different from a classical concept of kinetic energy. Okay, but that's really true. That's why it's commonly called Einstein formula. Energy for a particle. Of course, how to make use of this energy is you have to be creative, kind of make atomic bomb or something like that. But the energy is there. Good. So correspondence between momentum and energy, that comes naturally. Let's think of more concepts. First of all, let's think of gradients. Gradient is three-dimensional vector. Doesn't make sense, so we have to think of four-dimensional gradients, which also involve derivative with respect to time. Okay, how to make a scalar from this gradient? Well, we just combine it like this. We take inner product of the gradient, and we've got the only invariant form, the scalar, which is called D'Alembertian. And this is an operator which is commonly found in wave equation for light for any relativistic wave. Good, so we just make it rather artificially by finding invariant with respect to Lorentz transform. As far as electromagnetism is concerned, we don't have to think about separate vector and scalar potentials. They're just united in one four-dimensional vector characterizing electricity. We need to talk about the currents. It will be useful in further treatment. Current, well, current and charge density appear to be, two sides of the same four-dimensional vector. Right, current conservation has to be scalar, so I just take a vector of current, vector of gradient. Okay, and that's gonna be 0, conservation of particle number. If you write it down in components, you immediately get usual continuity equation, conservation of particles. Wonder if you remember how does it look like. D rho dt plus gradient of current. Yeah, so that's current conservation, continuity equation, and Maxwell equation. Okay, there are 4 master equations in the book, in your books. There's only single equation in relativistic electrodynamics. Yeah, it's a bit of a progress taking into account the fact that in the original book of Maxwell there were 54 fundamental equations. Quite a reduction within half a century. Good, so what we see so far, it's a pretty funny way to deal with classical physics. Minkowski invariance gives us an expectable conjugation of physical quantities which didn't seem related so far. Some stupid workshop. Good. Let's see. Now let us try to get to quantum mechanics. Right? That was all classical. Let's try to get to quantum mechanics, where we have a wave function. Good. Eventually, funny enough, Schrödinger has begun to derive his equation already after the relativistic hype. By that time, all physicists have been trying to be relativistic. So he's been scratching his head, trying to derive relativistic equation. And at some stage, he just, I cannot do this, I'm too old, whatever. He was really quite aged by that time. I'd better stick to a non-relativistic version. That was a blessing for many, many generations. That's why we still have kind of comprehensive quantum mechanics, which I can teach to everybody. Maxwell equation, very nice evolution equation. Let us try to do it let's try to accomplish the problem Schrödinger had. Let's try to derive it in relativistic fashion. Okay, this psi is a wave function which depends on 3 space coordinates and time. I want to have a scalar equation. I want to have scalar equation. I understand how to make a scalar, and eventually it's only combination of the gradients, which is simplest combination of gradients which you can move. Of course, I could do it to the 4th power, there's the Lambertian, but that doesn't make sense. That would be simplest equation and should hold. However, there is an immediate problem people have discovered in this respect. The problem is the energy spectrum. You have second order derivatives, so actually if you rewrite it for a plane wave, if you substitute p squared to space derivative, if you have time derivatives would give you p squared. So the solutions for energy at any given momentum, there will be two, with plus and minus sign. That's not what we see, right? So that was a problem people have encountered. That's why they were not satisfied with this equation, which is called Klein-Gordon equation. Moreover, if we look at probabilities, if you'd like to interpret wave function as a probability, then the solutions with negative energies should have negative probability. That was unacceptable, and people kind of stopped at this point, trying to get a better sense of it. Let me perhaps spend a minute explaining what stopped them. I skip all these messes, all the C's. Let me write an equation which I had. Okay, it has two solutions. But come on, we know how to deal with this already at school. If you don't like solution with a negative energy, you just present it as do you remember the sunny day at school? You don't want this solution. Okay, let's keep it. That's the equation I would come up with. And that's fine. It has only positive solutions. What is wrong with this equation? Who can explain me that? Look, in momentum representation, it's perfectly fine. The difficulty arises if you go to coordinate representation. If you would have p squared here or p to the fourth, that would be local. Derivative with respect to x. If you'd like to transform this guy, the resulting Fourier transform will be non-local. So there will be some kernel eventually, kernel K, which depends on x prime, at the same time moment. But that would contradict the relativity principle. It would mean that we can transfer information faster than light. So that doesn't work. But a kind of a school day idea about making it a product of two factors and skipping one, that healthy idea which we learn when we're kind of young and optimistic, that idea eventually won in a bit different fashion. That was a construction proposed by Dirac. Remember, young guy, he probably, it was probably fresh in his mind that a squirrel dies trick. That's what he wanted to achieve. Take this operator of Klein-Gordon equation and present it as a product. And then skip part of the product. It does work with numbers, but perhaps it will work with some other operators, which are square roots of the Lambertian. There are many square roots which you can take from an operator, and whatever, the only criterion, it should be kind of doable, it should be nice, and of course it should satisfy Lorentz invariance. Okay? Then that's what Dirac has offered to us, was just appeared in his mind rather mathematically. And this square root is solved in the following form. Okay, it is proportional to the first, to the derivatives. That's natural because squared of it contains two derivatives. And it involves some strange objects, yet unknown. And the multiplication of these objects has to be arranged in such a way that, okay, w squared is indeed the Lambertian. Okay, if you write down this equation, you see immediately what are the properties of these objects. Namely, the commutator of two Dirac matrices should be like this. It resembles commutator of field operators, but it is not. Those are no field operators, just some objects introduced by Dirac. Dirac gamma matrices. Okay, then after understanding that, he just got to the library, checked mathematical books, and he has figured out that minimal representation of these operators, objects, are 4 by 4 matrices. That's what we got from math books. It's not 2 by 2, not 3 by 3, not 7 by 7. Minimal representation is 4 by 4 matrices. Fine. So he has just taken these matrices and put them into equation. So what does it mean? It means that operator in the equation is 4 by 4 matrix, which contains gradients and time derivatives. And the wave function itself is also 4-component quantity. It would be kind of tempting to call it a 4-vector as well, give no such luck. It's not a full vector, despite of being four component quantity. It's called bispinor. Perhaps four gammas form a vector, also not such a luck. It's a different representation of Lorentz group. It's rich in representations. What would be useful for us that this combination of two bispinors and the gammas is in fact vector. Okay, let's make eight-minute break at this point. All right, here am I again. So we're here. That's Dirac equation, or equations, because of four, in abstract equations, in terms of gamma matrices. And that's a choice of gamma matrices which satisfy all multiplication rules they have to obey. Good. So what we have found is that time-related gamma matrix, gamma 4, is a diagonal matrix, 4x4 matrix with diagonal blocks 1 and -1. All right. As to three other gamma matrices, it becomes, I would perhaps call it three-dimensional vector for simplicity. Three-dimensional vector of Pauli matrices. They are arranged in blocks like this. Pauli matrices, they are related to spin. So that's how spin arises naturally in the formalism of Dirac, but of course it's not everything. Spin has two components. Spin gives rise to two components, and we have four. Okay, now we substitute these gamma matrices in this form. That's kind of usual form of Dirac equation. What I have here, and that psi A, psi B are two component quantities. So in total, we have four component bispinor. Right, so we have explicit form of the question. Let's look at it, let's solve it. First of all, to make the link to what we have already known, this is a Hamiltonian equation that makes lots of simpler if you believe in quantum mechanics. So how to make it Hamiltonian? Well, we just multiply it with gamma 4. So then this matrix which comes with derivative of x to the 4 just becomes diagonal matrix. And this is just derivative with respect to time as in Schrödinger equation. Here we have 4x4 Hamiltonian with the matrices defined like this. So there's no problem with the Hamiltonian, and we can have standard time evolution which satisfies all relativistic constraints. In fact, it comes good. Right, let us try to find the solutions. Let us understand first how to look for solutions, which solutions we want. First of all, we have kind of no potential. We have absolutely uniform space-time. That implies that we can look for solutions in form of plane waves. This is a kind of relativistic form of these plane waves. What will happen if I write it in non-relativistic form? It's about the same. That's something which we know. Let's see, what was that? I could put H bar for decorative purposes, and as you remember, there was energy coming like this. Okay? Time. Always forget time. Fine, sir. This is how does that look like in this form? In relativistic notations. Fine. What I want to mention that all solutions of Dirac equation are also solutions of Klein-Gordon equation. Right. To remind why do we do so? Okay, that we had two factors that we used, that we don't. But if you kind of multiply 0 with a factor, we got 0 anyhow. So all these solutions are solutions of Klein-Gordon equation. What does it imply? Again, I skip velocity. It implies usual relativistic law. But we would like to determine the whole vector and not just the modulus of it. All right, sir, that's an equation we have to solve. Right? Sir, 4x4 matrix equation. Did you get it? We have started with differential equation. We make substitution in the form of plane wave. We ended up with an algebraic equation for a vector. Good. Let's make it explicit. Four blocks. To find eigenvalues, to find energies, you can compute the determinant of this matrix and set it to 0. That gives what we expect. The rest requires some work. Let us see. We don't throw away solutions with negative equation. We just keep them. It is convenient to do the following substitution. If energy is positive, we express psi b, v of psi a. If it's negative, we do it otherwise. All right, so in that case, if our particle is at rest, it just becomes 0. right? So for positive at rest, psi b is 0. For negative, psi a is 0. It's kind of a way to separate the equation into blocks, at least at rest. Good. Then it still does not define the solutions uniquely. You still can make a choice. And the choice is to recall what we know about spin. We could take some spin quantization axis. We can take the solutions corresponding to z plus minus 1. Right. With this, we find 4 solutions at rest if momentum is 0. They're simple enough. We just have one in 4 different places. Here it's spin. Here as well. Here the difference is just a component of spin. Right. For moving particle, it gets a bit involved. We can find this, we can normalize it. It kind of doesn't look very much comprehensive. In next slide, I will show perhaps more comprehensive view and kind of how to get it to this more comprehensive view. Well, first let us let me pay attention to the fact that my choice of z-axis, spin along z-axis, was completely arbitrary and perhaps stupid. I would rather try to choose more natural spin characterization axis. Well, if you're dressed, you don't have anything which defines your choice. But if particles move, then it is natural to choose spin quantization axis in the direction of movement. So there will be spin either in the direction of momentum or opposite. With this, we can transform this into 2 numbers. So there are 2 polarizations corresponding to plus and minus this number. Good. And let us make parameterization of momentum in terms of chi. So if chi is 0, we are at rest. If chi increases, we accelerate faster and faster, approaching speed of light. Good. And we find 4 independent solutions of this sort. The difference here between that and that, it's the direction of orientation of spin with respect to momentum. Okay, but still there are 4, so there are different. So at chi 0, they concentrate either in this block or in this block. Fine. Did I say, yeah, what I also wanted to say now, it is in fact a matrix, right? We have found 4 solutions. For vectors, we can arrange it in a matrix. This matrix will show us how a solution is transformed from a reference system at rest to moving reference system. So, in fact, what we have done now, we have computed a Lorentz transformation matrix for the spinor, which is different from what we wrote for a vector, but that was promised. Yeah, Bispinor is not a vector despite having 4 components. Good. We have done with a Dirac equation for single particle. Fortunately, Dirac didn't stop here, and he gave us some new view, which apparently is not new for us. I guess you have heard about this many times. But let me first emphasize the problems which arise from the fact that we have negative energies for relativistic particles, for instance, electrons. Electrons are described by Dirac equations, that's for fact. Let us see what would be interesting features of electrons in this world. Each electron will be a source of infinite energy. Well, suppose we have some electron at rest, it would interact with some other particles, it would stop, it would go here, losing its energy, but it's not the end. Somehow it would be able to tunnel down, and then it would accelerate, lowering its energy. So electron would go faster and faster, and we get more and more energy out of that. That's really kind of cool. We could feed all our electricity problems with a single particle. That doesn't happen, and now, hoppa, construction of Dirac. So that already next level, right? For this, you need to know advanced quantum mechanics. You want to treat the solutions as levels for particles, and these levels can be either empty or filled. There's no single particle anymore. Right, so he just said that all states, yeah, it looks very simple. For us, it was pretty much non-standard thinking about that time, that all states with negative energy just plainly filled with electrons, right? That forbids the energy loss, that makes it impossible to extract infinite energy from a single electron. It just doesn't go there because all states are filled. So it becomes new vacuum. It is full of particles and full of charge. Now we encounter a problem because our vacuum is charged, and we know that charge produces electric field. So we're kind of in a center of infinite ball of spread charge. We should experience, well, actually, infinite electric field. Please solve this paradox for me.
So you have the same
not yet. We don't have positrons yet, but we just look at the vacuum. Positrons are excitations, right, at the background of the vacuum. Let's solve the problem with the vacuum. It appears to be charged. Have you heard of protons? Right. So then there's another fundamental field in our world where particles have positive charge and electrons have negative charge. So these two charges completely can be the same. We don't know why massive particles in vacuum do not produce gravitational field. We don't know yet precisely, that we cannot answer. But the problem with charge we can sort out very easily.
You also need to have the same number of protons as electrons, right? At least in the vacuum or below the vacuum. Is that
What's a number in vacuum? In fact, it's infinite number. It means that all states, all possible states are occupied.
do they have the same number of total available states?
Yeah, but this is natural because what you do to determine the number of possible states, you just take a big box, make wave vectors discrete, count them. This procedure doesn't depend whether you do it for protons or electrons. So there must be the same number of states to fill. Quantization of wave vector is the same for any particle. Right, so shall we move to positons? Yeah, okay, let's do it regularly with second quantization, similar to what we did for different vector, for instance, for metal, right? First of all, let us define creation apparatus. So for each discretized wave vector momentum, we have 4 possible creation apparatus. 2 spin components and 2 energies, positive and negative. So in total, it will be 4. Good. Then we want to arrange ground states, and as promised, we need to fill all states with negative energies. So that's what I did here. Negative energies with plus and minus spin. All right, so that's I have the basis, I have the vacuum. What can I do with this vacuum? I can, of course, create extra electron. That's it, with positive energy. I can also annihilate a particle with negative energy. The resulting state will have positive charge, and this is what is called positron. A particle which has the same mass that electron has and has the opposite charge. It was fine to see that it was fun to trace the trajectories of these particles in magnetic field, because yeah, they would have opposite circulation with the same, if they move with the same velocity. So there's magnetic field applied to this. Electron would go like this. and positron would go to opposite curvature. So that's why eventually how they observed experimentally as divergent trajectories in electric field, precisely symmetric trajectories. Fine. So it was purely theoretical prediction, and at some stage, I guess in 5 years, something like that, there was experimental confirmation, and that was a great boost for all modern field theory, for the way we understand the structure of fundamental fields, elementary particles. I shall perhaps say something which is less pedagogical. That prediction was not in original paper of the back, as I mentioned sometimes. So great people also have great mistakes. It was written in an original paper of Dirac that this particle, this positive charge, is actually thought. It came out of blue, and it has very different mass. It cannot be counterpart of an electron. That's somehow the temptation to explain everything in one hit was too big. But okay, he understood it, and people understood it very quickly that it's not actually important. Right, so that's how we accomplish the second quantization of in the framework of the Dirac equation. Right. I want to mention here something what kind of my supervisors told me many years ago when that time I decidedly wanted to do fundamental physics, theory of elementary particles, and they took me and said, look, condensed matter physics is eventually much, much richer and much more interesting. Right. To show it, I just put several spectra. That's spectrum of Dirac electrons, relativistic electrons in vacuum. So what we have here is two branches, and this branches field, and this is branch for electrons. So we have a gap between branches, which is mc squared, electron mass, so it's like 1 megavolt, mega electron volt. Right. If you take some semiconductor, you would have a kind of, to some extent, same picture. And we have a gap of a different scale. We have some complex splitting of the bands, also fun, deviation from this hyperpolar shape. Yeah, but in fact, the structure will be the same. All the states are field. Excitations are holes, which is analogy for a positron. Massless particles are called neutrinos, and they have conical spectrums, so there is no gap. If we make a graphite layer, you would see the same spectrum in condensed matter in two-dimensional space. So that kind of shows that as far as our reasoning is concerned, there's no much difference between physical vacuum, between theory of empty space, and description, understanding of any material. The same concepts apply in both spheres. Right. Where we are at the moment we are dealing with non-interacting electrons, which is a bit too abstract. So let us understand how to make them interacting. Oh yeah, I wanted to discuss yet a couple of things. What are possible transitions involving electron and positron? It's already interaction, so it's a bit ahead of what I wanted to say, but it's something which one can easily imagine. Suppose we have a photon of big energy. In principle, there is a possibility, if its energy more than this 10 to the 6 electron volts, that it would occasionally break into electron and positron. So we would have a photon decay into particles. That's something strange to imagine. What makes the word harmonic, what makes the high energy photons resisting, is the fact that this transition is forbidden by momentum conservation. So if all particles have relativistic spectrum, it just doesn't go. It is different if we could combine electron and positron together. In this case, it is a chance to emit electrons. So these particles can annihilate. But it also depends on the mutual momentum with respect to each other. If they're stressed, that doesn't work because the resulting photon would have to have zero momentum. And since it has finite energy, it's impossible. Very philosophical question. Why do we see electrons in our world and not positrons? Since they're kind of alternative particles, alternative excitations with the same mass, kind of naively we could expect the same amount of positrons and electrons in our world. We don't see it experimentally, although we haven't checked fuzzy galaxies, but everything which we see is made of electrons. Light leptons are electrons and not positrons. Good. Kind of popular explanation is that spontaneous symmetry breaking. So the symmetry has been broken because our work has been created with snap of winners, and its properties are defined by random fluctuations, which has happened in the moment of creation at 31st nanoseconds of that universe. that most reasonable explanation which I have. Right. Interaction. There has to be some elegant way to derive the interaction between electrons, or, which is the same, interaction between electrons and electromagnetic field. Let me remind you the concept of gauge invariance. If we take, for instance, non-relativistic Schrödinger equation, we can transform wave function like this, and right, if we, for transformed wave function, there will be an addition to gradient. If this addition to the gradient is pure gradient by itself, nothing happens. But if it's arbitrary vector, all right, then it is potential of vector potential of magnetic field. In the same way, we can deal with Dirac equation. This is the equation, and we can transform wave function, ascribing it a vector which depends on some scalar function. Here we have 4 vectors coming with a gradient. And as far as this vector is a pure gradient, it's precisely the same physics. The trick is to make it an arbitrary vector, arbitrary for vector, right? Which is associated naturally with a 4-component vector describing electromagnetic field, 3 components of vector potential, 1 component for scalar potential. So that kind of elongates the derivatives. It gives an addition to each derivative involved. Fine. So now we have Dirac equation of an electron in electromagnetic field. At the moment, electromagnetic field is classical, and there is a single particle described by wave function. But with our knowledge of advanced quantum mechanics, we know what to substitute, how to fulfill all these concepts. We need to take what we have learned about quantization of photons. So scalar A becomes a field operator in terms of photons. And well, there's usual Hamiltonian corresponding to creation-relation operators of photons. What was that? H, C, K, and that's going to be K. We need to second quantize electrons. And we need to substitute into the Hamiltonian all these electrons and bosons. That brings us to quantum electrodynamics. That allows us to draw a Hamiltonian. Fine. The Hamiltonian is complex, you cannot just solve it. So as a next step, people have attempted perturbation theory, and that was a very difficult period of doubt in theory of quantum fields in particular, and in theoretical physics in general. What was the problem? You can write kind of perturbation terms, but you immediately see that integrals which are involved diverge. There are divergences which are called ultraviolet at very big energies and momenta. There were divergences which they called infrared at small energies and at small energies, small momenta. So for any practical work in electrodynamics, they had to invent very tedious ways to cancel these divergences, to sum up perturbation terms in such a way that the answer, the divergence cancels from the answer. This is the concept of renormalization. How can I formulate it in words? We discussed a bit about renormalization. There are bare parameters and dressed parameters. So, for instance, electric mass, which is in the Hamiltonian, is bare. The mass which you see in experiment is dressed. And eventually, strictly speaking, this mass is infinite, bare mass, while the rest mass is undoubtedly finite. This was very unusual for theoretical physicists of that time. It took like 15, 20 years to swallow it and to elaborate the methods and to get used to it. Yeah, but that brings the concept of renormalization, which is still, since that is widely used and which allows us to understand quantum fields in relativistic world. And that difficulty, all because of that we don't have the smallest length in this universe, or at least we have not found it yet. In condensed matter, it becomes so terribly simple. You just have a lattice constant, and this works as a natural cut-off. You don't have to think much about renormalization. It all comes naturally. So, to summarize this lecture about relativistic quantum mechanics, I never regret that I didn't go to this field. Condensed matter physics is much more interesting. Fine, I guess I'm done with this lecture and with the whole course. We will still have online explanation homework session, which will be scheduled online if you want to attend. there will be opportunity to ask questions about exams. Do you have any questions about the course? No, we still have a couple of minutes. Fine. Thank you very much for attendance. Pleasure to see you. The lecture is over.
Thank you.
Thank you.